I'll get started. So my name is Divya, and I work at Adobe. I hope you all can hear me, and I tend to move around a lot, so if you can't hear me, just shout out. So I am the person keeping you from your lunch, and I will promise to be short and hopefully also informative. And today I'm going to be speaking about using hardware acceleration correctly with CSS. Basically, a lot of times, browsers have recently started using what is known as the GPU for doing a lot of animations, and they do so with CSS properties. And as front-end developers, we don't quite understand how that works. And so today, I hope you can learn a little bit more about that. So before I go further, I would like to explain a bit about why I'm here giving you this talk. Is that I work in a team at Adobe known as the Web Platform team, and the URL there will give you information on what our team is about. And most of what we do at Web Platform team is not just about making sure the browser as a medium is more consistent, which is also something we do with Chrome, Safari, and Firefox. But we also contribute new features, and ultimately our goal is to make the web awesome. And so I even bought this domain name, and it redirects to our open source stuff, so makethewebawesome.com. And so some of the features that we contribute to look like these. They are like regions, which allow text to wrap across containers, shapes, which help text to be wrapped within any possible polygon or shape, and the next two, which are italicized for a reason, is because blend modes, which you have seen in Photoshop, like overlaid and darken, saturate, lighten, and so on, and filters, which is basically the sepia and blur and stuff. These two features that we work on has worked deeply with the how the browser interacts with the GPU and how particular areas of your page get accelerated and so on and so forth. So the team, my engineering team, knows a lot about this, which is why because like secondhand smoking, I also get to know a lot more about these features than when I was a web designer or developer. So, as I mentioned, this GPU is pretty integral to what is happening on the web today, and my team has more than a passing knowledge, which I am now going to hopefully have you also have. So ideally what we want to do today is to change our knowledge, like basically change our understanding of what browsers are and how they work. And the way we usually operate with browsers today is, we write some code, and then there's some black box, and then something gets painted on the screen later on. And so we don't quite know what happens that converts the code we write to those pixels on the screen. And what we want to do at the end of the day, at least end of my talk, is that you see the code you write, you understand how browsers understand your code, and then finally you understand why things get rendered on the screen as they are. So ultimately, when I was a web developer, I never thought of browsers as something similar to a video player. Like, I mean, how many of you think browsers are like video players? Nobody. Or maybe you're just too bored. But anyways, the point is most of the browsers ultimately just paint pixels on the screen. And we don't understand that. At least I didn't. I thought browsers, there's DOM and stuff, there's vector and things. But ultimately, they're just a viewport. And then the browser just paints those pixels on the viewport. So for example, this presentation is in HTML and CSS and stuff. So you see there is this blue color. And what the browser is doing is that it's basically painting every pixel on the screen blue, except for a few pixels, which are white in color. And then there's a pattern to those whiteness that you see that makes sense as glyphs. And then when you put those things, because you understand Latin script, you see there's characters, P-A-I-N-T. And if you understand English, then you understand that it stands for a word, and it says paint the pixels.
I do this every day.
So how do those pixels render? Like, how is it that the browser understands the HTML and CSS, the JavaScript that I write, and how does it know how to render those pixels on the screen? This is like an image that I have stolen from the Chrome developer team. Most of what I'm going to show is stolen from the Chrome developer team. Yes. So this image here is basically how browsers render those pixels. And I'll be going through this almost every other slide. So first, the browser contacts the server. So you have the local host or your domain that it accesses. And then it gets a lot of bytes back. And then it starts reading each of those bytes and trying to start making sense of it. So it sees an opening bracket, then it's like, oh, it's an opening bracket. Then it reads the characters HTML, and then the closing bracket. And then, oh, that's HTML tag. So then it's like, oh, OK. So I probably need to create a DOM node representation of this and starts creating the tree that you first see on the left, which is the document object model. So it creates that thing for each of the elements that it finds on the screen. And then finally, then you have the styles that come up. And then it's like, oh, these elements need to be painted on the screen. I need to know the width, the height, the color, the background, and all of that too. So what it do is it'll look at the styles, and then it starts matching the styles to the DOM nodes and says, first of all, it needs to determine if that DOM node is to be rendered on the screen. For example, you may have a style display none on a DOM node, which means it will not be displayed on the screen. So it need not be in this next tree that it creates, which is called the render object tree. So the next tree that the browser creates is based on the styles that get applied to each DOM node. It could be like your style sheet, it could be inline styles, and so on and so forth. So the render object for, there's no one-to-one mapping. This image is too perfect. So there's not one-to-one mapping at all. So if there's a DOM node that is supposed to be displayed, then the render object is created for that DOM. And then the render object contains many things. And the two things that happen is, first of all, it needs to calculate the dimensions of each of the elements that needs to be displayed on the screen. So like, what's the width, what's the height, and what is the color and everything. All of those styles need to be calculated. And that's the values that will be saved in the render object. Now, the way it would do this is the browsers, oh wow, this is too big. The browsers would first need to calculate what's known as layout or reflow. So this is the point where it will calculate the styles, and then it will assign like boxes like for each of the elements that's to be displayed on the screen. So the offset width, offset height, and all of those things, it needs to calculate those values and save them to the render object. Now, you may think this is fairly trivial. It'll only happen during the beginning when it's a request for a page. But that doesn't quite happen, because it not just happens at the beginning when the page is being loaded, but it also happens when you change your styles for a particular element. So maybe you're adding a class name, or you're removing a class name, and then maybe you're adding some inline styles, and some third-party script injects those styles. Then those style changes will also cause the layout to happen. And then the other thing that will cause layout changes to happen is when you fetch layout values or scroll values. And this is something not many of us keep in mind, because when the browser has to read a width or an offset width, then the browser is like, oh, I don't know the value right now, so I need to recalculate the layout for that element. And when it has to recalculate layout for that element, it will also do for the child elements. And so it's like a lot of work the browser is doing to finally arrive at a value that it can read. And then only what you do at the end, as typically, is set the value again, and then it'll set the value again and go through the same process. The other way you can cause layout to happen is when you add or remove elements from the DOM. So when you add an element, and if your element is to be displayed, then its render object needs to be created. So it's the layout values need to be created, and then maybe it'll impact elements around it. So those values may change, and that also needs to be modified, and all of that will happen. Same thing with removing elements from the DOM. If it is already being on the screen, if you remove it from the DOM, then the values of the elements surrounding it will be impacted as well. So as you may begin to realize, there's a lot of calculations that happen every time you remove or add elements or change the styles. So ideally, especially when you're working with the rendering performance, you want to minimize this kind of layout calculations. And the way you would want to do that is, if you could move the content away from the flow. So what that would mean is maybe you want to position it absolutely or something like that so that when it changes in value, it will not be affecting the elements around it. Or you could also use it only on the element with the least amount of children so that the layout calculations impact the least amount of elements. So instead of finding the height of the body element, because if you do that, it starts to recalculate the values of the dimensions of all of the child elements of the body. And suppose you have 400 elements, then that's going to be a lot of calculation. So instead of doing that, maybe you want to find out the value of the height or the width of the last element in the body. And so that will impact only the child elements within that last element and not the whole body element itself. So the other thing that everyone, I'm sure by now knows about is to use request animation frame, which is, you got to use request animation frame. Everyone knows what request animation frame is, which does not fit this frame. And ideally, you would want all your browsers to render, as I mentioned, your browser is like a video player. So you want all the animations to happen at what is known as 60 frames per second. And if you want to know why this magic number was arrived at, there's a very interesting bit of history that Jake Archibald goes through in this talk that is linked to from this text called Rendering Without the Lumpy Bits. And he talks about how we arrive at 60 frames per second. But what this means is the browser changes an area, whatever needs to be changed, every 16.67 milliseconds. So the change needs to happen at this point. So if you're doing animations with CSS, this is what happens naturally. Like browsers would do this by themselves. But if you're trying to do animations with JavaScript, there is no default way, like there is no natural way in which you can do so with browsers. So typically what you would do is you set interval or set timeout. But doing this would actually drop frames if it's not synced to the browser refresh rate. So here's again another slide I stole from the Chrome developer team, which is that basically on the top is the display refresh rate. And you're like, oh, let me set the set timeout to 16 milliseconds, so I will match that refresh rate. But what you will see at the end is here, if you notice there's a red cross here because this frame is dropped. So you'll have a jerky animation. It will not be smooth. And you are like, oh, it's OK. I'll make my set timeout interval smaller. And all you can see is a lot more dropped frames. And it's not even dropped consistently. So you have a very variable performance. So it looks very, very jerky. And it's not smooth. OK. So when you say, OK, request animation frame, that's great. But even when you use request animation frame, if you are reading and writing layout values for every request animation frame event, then that's also going to be causing jerky animations. So here's this demo that was created. Like this has like 400 DOM elements, I don't know, even more. And then this is using request animation frame. But if you notice, it's pretty jerky. It doesn't look quite smooth. And that's because it's reading a layout value. So it's reading like an offset width and setting the style property left for each of these balls. And that is causing a performance hit because that takes a while. It has to recalculate for each and every one of these elements. So the easier way to do it is to not read and write for every request animation frame. And that's what happens here. We are just writing once, and which is why you can actually see the sine curve in action, which is much, much smoother. So once the browser does the layout, like it calculates all the dimensions, it finally has to paint on the screen. So the browser will say, OK, I need to determine which of these pixel values has changed, and I need to paint those areas of the screen. So if you move an element from left to bottom left to top right, then it needs to, and you're not animating, you're just simply moving it. And then the browser will say, oh, this area on the bottom left needs to be repainted, and this area on the top right needs to be repainted again. And so the browser does the painting. And so when does this painting occur? I mean, it happens all the time. But before we go there are two ways you can paint. One is simply to paint an element, just what element exists. So if there's H1, there's a text, then it needs to paint that text in the font that you specified, so it'll do that. But there's the other painting that happens, which is to find out when two elements overlap. And then, you need to paint one element on top of the other. So if you have an element that has a z index of 10, and it needs to be painted on top of the body element and whatever is the child element of the body. So this is another kind of painting. This is what typically is known as compositing, and I will look into that a little bit later. So the painting happens all the time, and here is an example of how paintings would happen. So if you go to Chrome Canary, you can go to General, and you can do Show Paint Rectangles. That's on rendering. And then what I can do is when I do the selection, what this red area shows is what the browser is actually painting, the area the browser is painting. So because I selected a text, then it needs to apply the blue color for the text that is selected. So that area needs to be painted, and that's what's happening. So when I hover, it will be repainted, and when I resize, redraw, all of the times, some areas will be repainted. So essentially, painting happens almost every time. So again, as I mentioned, this is our favorite illustration that you will be seeing all the time. So typical painting experience, I mentioned there are two kinds of painting. The first is to just paint an element. The other is to find the overlapping areas and paint that element on top of the other. And to find out these overlapping areas, the browser, once it creates this render object tree thing, it'll create another tree. So what the other tree will contain is what is known as render layers. And we look at what these render layers are next. So basically, render layers are created because of what is known as stacking contexts. And stacking contexts are things that have been in existence for a very long time. Because when you have an absolutely positioned element, it creates a new stacking context. And that's something, there's a long description of this in CSS 2.1 spec, if you're interested. So each of these stacking contexts create a new render layer. So traditionally, before this GPU thing came along, this is how you would create, how browsers would, say it'll create a new render layer. So first of all, if it's a root element, it's a HTML element, that will be a new render layer to begin with. So that will be the parent render layer. And all the child elements will be part of that render layer. So that render objects for those elements would be part of that render layer. So it'll be, in that same layer. Until it comes across a child element that has an absolute positioning or a relative positioning or a fixed positioning. And then it's like, oh, that requires a new layer. So I'll put it in a new layer. So then it'll be a new render layer that's the child of that parent render layer. And then again, the same process happens and for each of these properties that you set. So if you have opacity in CSS that's less than 1, then because it's translucent, it needs to show what's underneath, which is why you'll have a new render layer created. And similarly, when overflow is set, when you have overflow scrolling, it needs to show a scroll bar, which is why it'll create a new render layer. Now, the thing where the traditional stacking contexts work is that after all those render layers are created, what happens is the browser tells the CPU in your computer to, hey, paint all of these render layers using these calculations to one bitmap on the screen, which is the viewport. You just paint it to that area, and that's it. So that's all the browsers used to do. So depending if you scroll, then the browser will say this bottom area needs to change, or the top area needs to change. So paint that area alone, and the CPU will go ahead and do that. But because of the GPU, there's something that happens that is different. And now we have a different way browsers do these paintings and renderings, which causes us nightmares. So before I go there, I will skip through some slides to just talk about the GPU. So my first introduction to GPU was this stupid game, because I was in university 5 or 6 years ago, and then people would talk about some graphic drivers that are super cool that enables them to play all these games in real time, and they can be better at it. And that's how I was like, oh, GPU, okay, I understand what that is. So what GPU basically does is it's almost like a CPU, which is the central processing unit. And if you studied computer science, unfortunately, like me, you would know more about this. And so what the GPU would do is it's just optimized for processing large amounts of data in parallel. So it's like, if you have a lot of intensive calculations, then the GPU is better suited for it than the CPU. So now let's go back again to where we were. So when the GPU gets involved, then there are some of the new CSS properties will also trigger stacking context. So if you have a transform property on an element, now that would mean that element will be put in a new stacking context. So that will create a new render layer. And then if you have blend modes, and if you have overlay and all of those things on an element, then that will be put in a separate stacking context as well. And then filters. You have blur, you have sepia, and all of those image processing functions. If they apply on an element, then that will be in a separate stacking context. Now, what happens to these stacking contexts is, first of all, we are no longer restricted to one bitmap. So the CPU there's no just one bitmap to paint to. So the browser has multiple options. So there are some bitmaps the browser can say, hey, the GPU, go render that area. So this is the area, and the GPU has full control over rendering that particular area. And now, because we have multiple bitmaps, they are in different layers. So they don't impact the layers behind them or in front of them. So they just happen, all calculations happen to them in isolation. So now, because the browser has so many choices, the browser now needs to determine which of these render layers go into which of these bitmaps. So as usual, which is we have seen so far, browser solves these problems by creating yet another tree, which is the graphic layer tree. And I'm not going to show that, but it's very similar to the render layer tree, except it's now a combination of render layers into a graphical layer. So once it's created those bitmaps, now it needs to determine which of those bitmaps are going to be rendered by the GPU. And it's fairly sensible what browsers do these days. And what I'm talking about these days are definitely based on our understanding of WebKit and Blink, but I'm pretty sure what Firefox and IE do is also somewhat similar. I'm not sure if it's completely similar, but it must be somewhat similar. So the browsers determine which of these bitmaps are accelerated, because when intense painting occurs, for example, you have video, you have WebGL, you have Canvas, and all of these things, because it's the amount of data that needs to be processed and applied over the set of pixels is too large, then the GPU gets kicked in. Sometimes you have an element that is 3D transformed, and so if it's 3D transformed, then you need some calculations to find out what pixels need to be painted which color, and so on. So that would also trigger the GPU. And then you have all these new features like the filters, the masks, the blend modes, the reflections, the opacity. And you're animating through them. So if you're animating through these properties, the GPU is much more capable of doing these, because they are all image processing functions, and it's much easier to do it in the GPU than to do it with the CPU. So the browsers immediately start using the GPU for these things. And you have elements that are positioned with position fixed. So this means these elements are not going to move while everything else is going to scroll. So instead of repainting frequently, it would rather keep it in its own isolated GPU layer and then paint it when it's necessary. And every time the GPU rendered bitmaps, there is a content that's overlapping with the GPU rendered bitmaps, then those content will also be rendered by the GPU. So for example, you may have like a carousel, a 3D carousel, that's image is transformed, and then it's rotating, and then you have these arrow keys, they're just for navigation, but they happen to be on top of those images. And because even though they may not be, having any transforms, any of these animated filters, but merely because they are on top of these, GPU rendered bitmaps, they will also be rendered by the GPU. So how can you find out how many of these, how many GPU rendered bitmaps exist? Both Chrome and Safari have ways to do so. And here is one of these samples. So here is what Chrome does. I hope it doesn't crash. There's an experiment in Chrome Canary that allows you to see layers. So you go to Experiments tab, and you can do Show Layers panel. And as soon as you do that, you'll have a new panel on the right. Chrome developer, it's called layers. And what you can see here is you can see the layers that are being used. So this is pretty flat, it's no big deal. But once you start moving, you'll kind of see all the layers that are being rendered by the GPU. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 layers. And not only does it show all the layers, but it also shows why these things are using the GPU. So it shows it's because it's using 3D transform, and there's an overlap with an existing GPU layer. And then it shows you here, this layer is being used for clipping a GPU transformed element, which is why it's using, there's also all of these reasons. So this is in Canary. I kind of like what WebKit Safari also shows. This is much simpler, but it's a list of all the layers. If you notice, there's only 8 here. And it also shows you the reason for compositing and the same thing. So once you know how many GPU render layers are, this is something that's useful for you because while GPU is awesome, there is it is something that you need to be wary of. So the greatness of GPU is, first of all, once you render some elements with GPU, there's no more the painting and the layout thing, the calculations, dimensions, they all vanish. They don't happen at all because the GPU is just directly rendering to a surface. Like it knows the dimensions and that's all it needs to render to. So if an area is large, because GPU does parallel processing, it does, it splits those areas into tiles and only changes particular tiles that need to be changed. But obviously, this also means it uses a lot more power than typical. So it's than when you don't use the feature, which is kind of expected. But sometimes when you use the GPU, you will see that flickering happens. And this is something that you may have seen many times. There are 2 reasons why this would happen is that you have many tiles, and then one tile moves off screen, and then those tile gets destroyed. The new texture needs to be added to the tile. So then when it keeps swapping those textures, then it flickers. The other reason why this flickering would happen is that sometimes you are rendering an element with the CPU bitmap because there is no reason to use the GPU because it's just fairly simple bitmap. But then suddenly when you're hovering or you add a class name or something, or you add an element that is suddenly using a 3D transform, or maybe it's using one of those properties like filters and you're animating through that, then it needs to use the GPU. And what happens is the browser's like, oh my God, I need to use the GPU right now. So the CPU immediately communicates to the GPU, hey, here's this image that you need to render for now, and this is the animation you need to apply. And then GPU's, oh, okay, let me just quickly switch and use this area to show this change, this image, and then it does that. So here's an example that happens when you can see it getting animated. So here's an element, and you can see that flicker when I hover. And that happens because it's suddenly changing, going to the GPU. Now, it's very easy to fix this, is to put this element texture already in the GPU. And I can just do that by using our favorite trick. I would not recommend this, but if you notice, as soon as I typed it in, it flickered because that meant that element is now being rendered completely by the GPU. So when I hover, there's no more flickering. It's all smooth. So while GPU is cool, it is also limited by memory. And as soon as you start using GPU, your memory consumption will just rapidly rise. And I'll tell you why a little bit later. And then you're also limited by the communication that you have between the CPU and the GPU. So there's only so much the CPU can transfer to the GPU at one point. And if you're trying to transfer a lot of information, and then that communication channel throttles how much the GPU can do. So let's look at the memory. And so memory is basically your random access memory is where all the data that you use for your website, for your page, all the images that you use for your page, all the resources, all your scripts, the styles, the HTML, and your GPU textures are stored. So if you have an image and you 3D transform it, that means the image set is in the memory and the GPU bitmap of the transform that should be rendered. That's also in memory. So this is not a problem, and I can show you how you can see how much memory is being used. For example, here if you notice, the Safari tells you that for this layer, the GPU layer, it's using 7.3 megabytes of memory just for this GPU bitmap. So even Chrome does the same thing as well. So this is not a problem on desktop because, you know, in desktop you have a lot of memory. So, and even if you have a lot of memory, even on desktop, if you're approaching a point where your memory is too small, the operating system will warn you that, hey, you're reaching an area when, you know, your memory is too small, quit some applications, which is fine. But on mobile devices, there is no such warning. These operating systems automatically quit your pages or your web views or whatever to free up memory. And the other thing about mobile systems is like when you have a lot of apps open and then then a user opens your website, then you have much less memory to work with because all these other apps have already used the memory space that's available. And that's kind of constraining. So ideally, you want to reduce your memory usage as much as possible. And so you want to use smaller images, and because, you know, your image, the memory that's being used depends on the dimensions of your image and 4 bytes, because you need 4 bytes to represent a color value. You have red, green, blue, and the alpha transparency. And you also want to use smaller JavaScript file, CSS file. This is like typical, normal performance things that you mentioned earlier for performance tips. But the other thing you need to be careful about is that you only transfer smaller and fewer textures to the GPU, so that, you know, because you don't want to use so much memory, and because GPU is very capable of using a lot more memory. And you use fewer layers. Like we saw earlier how many layers each of your, each of those 3D transform properties caused. So you want to make sure that the number of layers that is created is as few as possible. Well, this is cool. There's the other thing that we need to look at, which is reducing the communication that happens between the CPU and the GPU. I'm sorry, it's getting clipped. But so when you are animating a 3D transformed element, and you're animating a property of a 3D transformed element, the CPU needs to communicate to the GPU what is the next image that needs to be seen next by the user. Now, this is not necessary for certain properties, because these properties the animation of these properties can be handled directly by the GPU. And these properties are called hardware accelerated properties. So you may have heard of hardware accelerated CSS, hardware accelerated SVG, and so on. So these properties will be handled directly by the GPU. So like opacity, transform, the animation of opacity, the animation of transform, the animation of filters, the animation of blend modes. And all of these will be handled directly by the GPU, which is why when we go to this demo here, as soon as we had that animation happen, it's just happening in the GPU. It's not communicating with the CPU. But if you are going to animate other properties like color, background color, or the width or the height of a 3D transformed element, then the CPU needs to keep telling the GPU what that next image will be. So that communication will also throttle the kind of smoothness that you may see in the animation of those properties. So it will cause a lot of repaints by the GPU, and you want to avoid that, because that means a lot of power consumption, a lot of memory usage, because you keep replacing those textures. So there are other ways you can, minimize the use of GPU. So don't try to animate the Z index, because that's like, if you looked at our favorite chart, you would know that the render layers determine the graphic layers. So if you animate the Z index, then it's going to change the render layer tree itself. So now all the textures in the GPU that are already there may get destroyed, and then you have to recreate this whole thing again. And then that's going to cause a lot of rendering performance bottlenecks. And then, as I just mentioned, don't try to animate non-hardware accelerated properties on GPU accelerated content. So Arya, who is also giving a talk, I think, soon, wrote this great article on this very topic, explains exactly what happens. And finally, a lot of times you may find yourself wanting to show and hide 3D transformed elements or GPU accelerated content in general. So when you're doing that, if you use, typically how you would do it is just display none and display block, or just add a class name, and or sometimes do visibility hidden and visibility visible kind of a thing. But if you do that to GPU accelerated content, then it's a lot more expensive. So ideally, you would just want to use opacity. And the reason is very simple, is that opacity is controlled in the GPU. So the textures, if you use opacity, those textures for those elements will remain in the GPU. So when you show and hide, there will be no flickering or no slogginess. It will just be showing and hiding from the GPU. But if you use the visibility hidden property to show and hide those accelerated content, then it removes the textures from the GPU. Then it has to be recreated when you use the visibility : visible property again. Now, display none is worse because it removes this whole element from the render object layer, which will mean you have to recreate some aspect of the tree in the render layer tree, and then finally the graphic layer tree. So that's a lot of work the browser needs to do. And the worst, obviously, is removing elements from the DOM, because finally here you're removing elements from the DOM, so the DOM changes, so all the elements get fired, all the events get fired. And then it does the style and dimension calculations for the elements around it that get impacted, and then it calculates the render layer, and then finally it'll do the graphic layer. So that's going to be really, really bad. So as I expected, I finished much, much, much early. And so in summary, what you need to be aware of is that rendering is kind of a beast. It's even worse than Wordor, and you dare not want to enter there. And if you are going to do a lot of work, just make sure you do what is necessary and no more and no less. And if you're using the GPU, memory will quickly get out of hand. You have a lot more, we have much less memory to work with. So you want to make sure that you do it right, and then you reduce the CPU-GPU communication that happens. And finally, there's also always browser tools that help you to test these things. So Chrome Developer Tools is pretty awesome in this way, and Safari is also not bad. And Firefox, I think they're still working on something like this. But you have these tools all ready to use and test, so you should go ahead and use that. And finally, if you are looking to know more about our work at Adobe Web, follow us on Twitter. So that's all I have.